Okay, so we have some honored guests here today. Kevin,
Hi.
Colin, and Chris. Kevin was kind enough to leave his spring up here for me. But now, what we're going to talk about today, we've talked about previously. Let's pull my notes out here. The fact that gravity, okay, affects mass. Gravity is created by mass. So gravity is both affected by and created by mass. The electric field is created by a charge, and it affects a charge. Okay? So again, it's very similar. The electric field is both created by and affects charge. The magnetic field affects moving charge. So what is going to create the magnetic field?
Charge.
Moving charge. Okay. What do we typically call a moving charge? What is a typical way that we can figure out what a moving charge is?
Current.
Current. Very good. All right. So now, it doesn't have to be it can just be an individual particle, but that's not going to be a very strong magnetic field at all. So what we want to do is take a look at currents. So we're going to come up with the formulation of what's called the Biot-Savart law. All right. It looks like Biot and Savart, but the Biot-Savart law. Okay. And this is sort of the F equals ma of magnetism, or the Coulomb's law of magnetism. What we're going to say here is that, let's just say we have some sort of line of charge here. Okay, that has a current I. Okay. So I look at a little section of that current. Let's just say right here. I'm going to call this ds. Now I'm going to give ds direction in the direction of the current. So my ds as a vector looks like that. Okay, it's going to point in the direction of the current. And I have some point here. It's over here. I'm going to call that point P. So I've got ds from right here, and r in the red there. So I've got ds that goes like this, r that's going like that. Okay. There's an angle, if I just extend this out, there's an angle between them. Okay. So now, if I want to figure out the magnetic field due to that little portion, now that's not the magnetic field due to the whole wire. That's just the magnetic field due to a little tiny portion. That magnetic field, that little portion of magnetic field created by that little portion of wire, is going to equal mu naught over 4 pi times I, let me just make sure I put this down right, ds cross r over r cubed. Now, let me tell you what mu naught is.
Good afternoon. Any spring team
Mu naught is equal to exactly, not close to, equals exactly 4 pi 10 times 10 to the minus 7. Okay, and you can prove this to yourselves here. Tesla meters per amp. Tesla meters per amp. So 4 pi times 10 to the minus 7. I can discuss with you why it equals exactly 4 pi. And if you notice here, these go away. The constants disappear, basically, and we're just left with 10 to the minus 7. It's very interesting that we have something that's exactly 10 to the minus 7. Interesting. Okay. There are reasons why that works out.
Just because of our arbitrary system.
Well, we didn't just back into it by luck, per se, but it has to do with the fact that electromagnetic waves travel close to the speed of light. If you look at K, 1 over 4 pi epsilon naught, 9 times 10 to the 9th. In fact, if you do 1 over 4 pi epsilon, well, figure out what K is exactly. It's not exactly 9 times 10. It's like 8.9. Take the square root of it. Tell me what you find. And then see if you find another number like that in the book. It's an interesting factor. All right. So now, a couple things here. Okay, we've got theta. So this ds cross r. That helps us find the direction. Okay. This cross product means that we're going to use a right-hand rule. Okay. So for the current that's right here, okay, our hands go along r. Our hands go in the direction, thumb goes in the direction of the current. Sorry, thumb points in the direction of the current. Fingers wrap around in the direction of the magnetic field. So everything over here is going to come out of the board. Everything over here, as this continues to wrap around, okay? So over here, it's going into the board. Here it's coming out of the board. So my magnetic field is going into the board over here. So it's everything over here is coming out of the board. But specifically, we're talking about at this spot right here, I've got a magnetic field that comes out of the board. Another thing that you might notice here is that that's very interesting that this is with respect to r cubed.
Did you say out of the board, you mean into the board? Do you have access?
Yeah, it's into the board. I'm sorry, I said it backwards. It's been a long day for me, even though I don't have a plug. Okay, it is going into the board, coming out up top here, into the board over here. Now, you might notice here that this is r cubed. Every other law that we've been doing has been r squared. This is still r squared. How can you tell it's actually r squared?
It's not on top.
There's an r on top, so this would cancel that r out. So this is an inverse square root. In fact, when we take a look at it though, it's going to drop to 1 over r because we do have a line of charge. Very similar to what we had with the electric field. Now, I'm not going to go through the proof. Okay, you guys can look on page 767 for the proof of this. So go ahead and take a note on that. That's page 767 for the proof.
I checked the square root, 1 over 4 pi epsilon.
Okay.
I got 8.39.
It's 8.39? Okay. Yeah. All right. Times 7 to the third. 10 to the
Negative 7.
10 to the
Unless I did something terribly wrong, and now it's
yeah, because
proven
square, because you
myself
have to
that I'm
have
an idiot.
9 times 10 to the 9th. Oh yeah, I have to multiply with something else too. But anyway, all right. So now, I was thinking of something else. But anyway, we have the magnetic field due to a long straight wire. I don't like let's just say long, which we write in parentheses infinite. Straight wire. That magnetic field will equal u dot I over 2 pi r. Now, you can actually prove that off of this, okay? But I'm not going to go through, you guys can look that up in the book. Yep.
Since there's no such thing as an infinite wire, why does that matter?
Long is a pretty good.
Okay, just long.
So as long as you're close, the approximation is as long as you're close to the wire compared to its length. So if I'm looking at this wire from here,
Yeah,
okay, not a very good approximation. If I'm looking at it here,
okay.
pretty darn good approximation. So now, we could also look at this. So if we have a long wire, and I'm looking at a point right here, okay, current's going like this. Now, right-hand rule, our thumb points in the direction of the current, our fingers wrap around in the direction of the magnetic field. So everything below this wire, okay, I've got a magnetic field that goes into the board. Everything on this side of the wire, I've got coming out of the board. I've got my dots. You can see it, so this has too much weight on the sides. So right here at this location, okay, my magnetic field comes out of the board. My distance R is the perpendicular distance between the wire and the dot. Okay? So if I know how far away, that could be little r or capital R, doesn't matter. If I know the current, which I'm going to say is current I. U naught and pi are constants, so I can figure out the magnetic field at this location. Okay? If I know the current, I know how far from the wire it is. And this is going off in both directions. By the way, we also have, for a semi-infinite wire, I'm going to leave VO_R out there for a bit. There's semi-infinite wire. I'll just make a little notation here, infinite. B for, I'll put infinite over 2. So in other words, I have a wire that goes like this, and I'm located right here. That's what semi-infinite means. Okay, it seems like a ridiculous term from a mathematical standpoint, but once you see it, oh, okay, that makes sense. So the wire is coming, starting here, going that way. And it could be like the wire here. You say, well, how can I make a loop like that? Well, the wire here is kind of current coming out of the board, and then it makes a right turn. So for this, all that magnetic field is for half of the one. Okay, if I do this, it's still X is up here, dot's up here. Okay, that magnetic field is just half of that. It's just mu naught I over 4 pi. Okay. So those are just some equations that can be useful. You're going to want to take a look at the equation sheets to see whether or not you have those on the AP exam. Take a quick look while you guys are writing that down. They've got VO_R. They've got all they have is VO_R and Ampere's law, which we can use to prove that very quickly, and then toroid. Actually, solenoid they have. And we'll find out what that is in a moment. But now, let's just say that we have a curved piece of wire. Let's just say that I have something like this, and it goes out of an angle like this. So my current is coming, it's coming in like this. And then it follows the curved path, circular path, like this, and then goes out. Okay. Now, by definition, I'm setting this problem up so my R is constant the whole time. So I have a current I that's coming in. Now, you say, all right, I want to figure out the magnetic field at this point, knowing my current is I. And I have an R. Well, first of all, one thing that we should point out, okay? If I take a DS out over here, okay, DS would point in this direction, and so would R. So then you have DS right here and R right there. These two point in the same direction. So if they're parallel with each other, what's the cross product? 0. 0. Okay. Cross product and parallel don't go together. They're 0. over here, I've got a ds that points this way and r that points this way, or the other way. In that case, okay, I should have r pointing the other direction over here, but in this case now, at this location, these are at right angles. Okay? So if that's the case, the cross product becomes it's 90 degrees, sine of 90 is 1. So what I'm left with, what that reduces to, all I'm concerned about is the magnetic field from here. This similar argument is here. I have no contribution to the magnetic field at this point right here. So now, dB will equal u naught over 4 pi I ds, and I'll talk about that in a second. This gives 90 degrees, r over r cubed, so that's going to be over r squared. Okay. Now, say IDS, okay? ds is just your arc length. R is everything here, r is constant, I is constant, u naught, i's are always constant. So all I'm doing is integrating over ds. It's the arc length. Okay? If this is an angle, I'll just say it's an angle phi. My magnetic field will equal mu naught over 4 pi times I. ds is arc length. That's going to be r times the angle phi in radians over r squared. Okay, so usually we write that together now. Mu naught I r. Oops. That r will cancel out. Mu naught I phi. Mu was over 4 pi r. So that's magnetic field from a partial ring. Now, let's say you had a magnetic field for a whole circle. That would be mu naught I. The angle would be 2 pi over 4 pi r. Pi's cancel. 2 cancels out here to 2. Magnetic field for a loop would equal mu naught I. Let's see. Over to yeah, we know that. I was just making sure. Sorry for mixing my capital R's and my lowercase r's. They are the same. Yep.
Why do you make dB over r squared?
Okay, why did I make this r squared here?
Yeah.
Okay, because this is ds cross r.
Yeah.
Okay, my cross product was
Oh, okay, you're right.
okay. The cross product. Okay, cross product goes away, so it's r over r cubed, which is r. So now, look at an interesting example. Okay, it's the force between two parallel currents. I have a current, which I'll call A here, and a current B here. Now, each of these, okay, this has whatever weight it has. Okay, this has L, and L is going to be the same for both. Each of these will create a magnetic field. Okay, current creates a magnetic field. Okay. The interesting part of the magnetic field that it's creating is where this creates magnetic field over top of this, and where this creates magnetic field over top of that. Okay. So the magnetic field that A creates, that B feels, the magnetic field that A creates is going to equal, okay, mu naught I over 2 pi r. Okay. Magnetic field that B creates, BB, will equal mu naught I. Now this will be IB over 2 pi, or whatever its R is. I should call this IB and IA. Okay. A does not feel its own magnetic field. Okay, the magnetic field here does not affect A at all. It does affect this one. Take a moment, use the right-hand rule, figure out the direction of the magnetic field at B due to A. Magnetic field at B due to A.
Does it work?
Okay? Thumb points in the direction of the current, fingers wrap around in the direction of the magnetic field. So it's going into the board over here. So my magnetic field over here are X's. Okay? Over here, B, the magnetic field that B creates at A, current B, magnetic field is coming out of the board. So around this, I have dots. Okay? So magnetic field that B feels is due to A, magnetic field that A feels is due to B. Okay. Now, let's look at the force on one of them. The force is going to equal I-L cross B. Now, L and B, I think we can see are right angles. L is going following the current, B is going like this. Okay, right angles. Okay, so this is just going to give us ILB. So now the force on A is going to be the current of A times the length times the magnetic field of B. Okay? A feels the magnetic field of B. Similarly, see that? The force of B is going to equal IB L times the magnetic field of A. So let's compare. The force on A is I, A, L. Now B, the magnetic field of B is going to be mu naught I, B, over, and let's just say that this distance right here, I should call that, I'll just call it 2, over 2 pi d. So I jumbled it all together. The force on A is equal to mu naught I A, I B, L, over 2 pi d. And what direction would it feel a force? Magnetic field comes out of the board. Right hand. Finger goes in the direction of the current. Okay? Goes like that. All right? So we have a force on this to the right. Think about this. This is the force on it. You should be able to completely predict the force on B right now. For every, going back to Newton's third law, which is something they like to peg on the mechanics section of the AC test. For every force, there's an equal and opposite reaction force. So, force A to the right here, we should expect it to be the same amount going back this way. So let's take a look. Current goes in the direction, fingers go in the direction of current, palm goes in the direction of the magnetic field, thumb points in the direction of the force. Well, FB has to go back this way and show that the magnitude is now the same. FB is is equal to, well, IBL, where's L, times the magnetic field of A, which is mu naught I of A over 2 pi r, which that r is d naught. Okay, so now I just rearrange. E is equal to mu naught I A I B L over 2 pi d. Same as I still see videos of from time to time. Same. So the force on A and force on B, Newton told us that they had to be the same. Okay, this is just showing that they have to be the same. All right, we'll shut it off there, and we'll do Ampere's law next week. I'll post the problem. Take a look at the website though, because I'll post the problems. I don't want you guys to do off that. We're starting to read out.